Okay, welcome to this week's hottest seminar. This is the second last seminar of the semester, and we are very happy to have Egbert Rijke from the University of Ljubljana, who will tell us about a higher encode-decode method. Please go ahead.
Okay, so thank you very much, Dan, for inviting me to this seminar. Yeah, it's a great honor that I can speak here this time. Yeah, I'm really happy that I can get a chance to speak, especially in this Corona time where we don't get to go out so much anymore and not go to conferences. So this is really great, and we get to see each other and chat a little bit. So that's nice. My talk is kind of it's very work in progress. So I will not really. I will prove some things, but I will not present any very big things. And I called it a higher encode decode method because halfway through the talk I'm gonna tell you of a theorem that should in principle help us to compute higher homotopy groups, but there will be a big caveat. I haven't actually been able to compute any higher homotopy groups using it, but I have just used it as a way to direct myself in further research, and I'm gonna tell you about that. So in that sense, this will be a hopefully inspiring talk, so that maybe you get some new approaches to computing homotopy groups in homotopy type theory. The first topic that I'm going to talk about is actually a little different, and that's because the way I started this particular research started with the talk from Jamie Vickery, who had a seminar in Ljubljana, also online, of course, and he showed us his globular proof assistant, and he did this synapses thing, and then I wanted to formalize it, and I didn't formalize it, but I have an informal proof, and then Christina came along and actually formalized it way before me. So she has the only formalization, but I thought my proof could still be interesting, and it was for me the motivation to consider even this higher encode decode method, because I was like, okay, I have this ellipsis now, and how am I going to use this to compute pi 4 of S3, for example? And that led me to think about this. So I'm just telling the story the way it started back in, I suppose it was in October, I started doing this. And then, so here's the overview of my talk. There are three parts. First part is the ellipsis. It will be my informal proof, but I hope it will be conceptually clear. Then there is this higher encode decode method, which is not exactly going to be a generalization of the ordinary encode decode method, but it's going to be another way of encoding a vibration over a type, so that you get the pi n of xn out of it, and no, pi n of x you get out of it, and to apply it, you need to know things about Eilenberg-MacLane spaces. So that's how it's gonna go. So my last part of the talk will be about some theorems about k is equal to n for all n. So that hopefully we get maybe another approach to computing pi 4 of S3, which is still not really formalized, if I understand it correctly, because Guillaume had this little technical gap in his proof about the associativity of the smash product, if I'm correct, and it's kind of unsatisfying that we get stuck on such a technicality that no one really wants to work on, and not so actively, it seems. Maybe people are working on it, then it would be good. But I'm going to sketch another approach in this talk. So here's part one, ellipsis. And I will start with the Ekman-Hilton argument, which is a theorem that says that if case is at least 2, then the Decode homotopy group of X is abelian. So this was, of course, proven in homotopy type theory using path induction and so on, was proven by Decode, if I'm correct, a long time ago. And you can find this result in the hotput, but let's have a look again at the proof, because the synapsis is something about this statement. So first, we recall that in the second identity type, there are 2 ways to concatenate paths. One would be, can you see my mouse wiggling here? Okay, great, then I can point. Okay, so one way to concatenate them is in the ordinary way. You have alpha and beta. They are composable because the codomain of alpha is the domain of beta, and so you have alpha beta. But the second way is you can horizontally compose alpha with gamma, and this way is defined by path induction. If you want, you can just say alpha is raffle, gamma is raffle, and then this composition should also be raffle. Given that these 2 composition operations are there is an interchange law that says if I first vertically compose alpha and beta, and I second vertically compose gamma and delta, and these composites, I'm going to horizontally compose them. Well, that's the same as first horizontally composing alpha and gamma, and horizontally composing beta and delta, and then vertically composing those. And the Ekman-Hilton argument is using this interchange law. So it's something about the second loop space. S and T here are identifications of raffle with raffle. So that means that they are in omega 2 of X, where X is a type. And then it says, if I compose, concatenate S and T, that's the same as when I compose T with S. So that means the concatenation operation is abelian. And that proof uses then the second composition operation. You can say, S and T, well, I can say they are horizontally composed with raffle, because that horizontal composition, of course, satisfies unit laws. And the same with T. Now I interchange. It looks like they didn't change much because S and T are still in the same position. But now we got in the middle this horizontal composition, and we apply the unit laws to get S composed T. So all we did here was to change one composition operation to the other. But we had progress, because now we can say, we apply the other unit law. So we put raffle on the left instead of on the right, and vice versa. And we apply another time the interchange law, and we undo with the unit laws, and we get decomposed with S. And that's how you prove Ekman-Hilton. And the way I like to think about it is a step from here to there to there. These are like the blocks of this proof. And now this ellipsis is the claim that if I now go from TS to ST again using Ekman-Hilton TS, then this concatenation will be raffle. So if I go from ST to TS to ST, then that's raffle. Let's see, there's a lot of ingredients in my proof, and my proof is very long, and that's why I was not able to formalize it yet. And Christina has a very short proof. It's like 100, maybe 200 lines of code, if I remember correctly. And my proof, I'm like halfway through, maybe I'm at this step. And it's already like 1500 lines of code, and I have one coherence law that took me like one only that took me 500 lines of code to formalize it. So it's like already one little ingredient of my proof is longer to formalize than the entire approach of Christina. So in a way, it's her proof is a million times better. But I don't know. This is what I have to say today. Okay, so
can we
yeah.
ask questions, or should you?
Yeah. Please ask questions, please.
It smells like path induction here. Is Christina using a clever path induction that you missed? What
Yeah,
makes it harder?
so I'm gonna generalize it in such a way that I can use path induction all the way, and then in some point it's just raffle. And maybe Christina found a better way to do that. I actually I haven't understood her code. Maybe if Christina is here, she could comment, or I can ask her. But that's indeed the approach here. This coherence law, but of coherence laws, is indeed something that you do with path induction all the way. Or you have so many free paths that you just induct them all, and then the answer is raffle. But let's go slowly through this process. So this is going to be about the third identity type. And in the third identity type, there will be yet another concatenation operation. I'm going to call it star instead of black bullet or white bullet. And even on the fourth identity type, there is a fourth concatenation operation. And you can, in fact, prove that on the with co-induction, you can show that on the nth identity type, there are n concatenation operation. And all of them satisfy unit laws, and all pairs of them satisfy interchange laws, and the interchange laws themselves satisfy unit laws because they're proven by path induction. And at least in the case of dimension 3, there will be 3 interchange laws because there's 3 pairs of operations out of the 3 operations. So there's going to be 1 coherence law. What I was saying about that. Yeah, okay, so you have the interchange, you can put all the interchange laws together in an even bigger diagram, so to say, and get the coherence out of them. And in the most general form, it's gonna look so ugly that I didn't even put it in a slide. But you can, I formalized this. And you can then simplify it to a nice hexagon that will be in omega 3. But the general form is really an enormous diagram. This one is just very long to write down. Even in my formalization, I had to break down the specification of the interchange law in parts, otherwise I couldn't get through it. And then the simplification is not just the statement will be simpler and it will be simpler to use, but to derive it actually is this was one of those cases where I had to use 500 lines of code to even get to the end, and so I did that. But and then you have to not give up. All right. So let's see the meat of it. If you have a binary operation f, and it takes an element from one type, it takes an element from another type, and it outputs in a third type. So this is the most general kind of binary operation there is. Then it has a binary action on paths. So if I have a path in A, a path in B, then I get the path in C. Oops, I don't know. So here, if I get a path from X to X prime, a path from Y to Y prime, then I get the path from fxy to fx prime Y prime. But the point is that path concatenation is itself of this kind. So it will be A will be path from X to Y, B will be path from Y to Z, and C is path from X to Z. So we can use this this binary action on paths to get all the higher concatenation operations uniformly. That's why you can also get them by co-induction and using globular types if you want to do that. The ordinary concatenation operation is here. If I get from x to y, from y to z, then I get from x to z. This one we all know. And at the level of the third identity type, it looks like this. I have a path from x to y and two of them. I get 3 identifications between those, and I get one to the other. Then I can concatenate them into a bigger tree cell from here to there. So that's one shape that you get. Now we use the binary action on paths to, oh, this is a black bullet, sorry for the typo, to get the next concatenation operation using the binary action on paths. From P is P prime, a path from Q to Q prime. Then I get a path from PQ to P prime Q prime, and this is the black bullet from the ordinary concatenation. And at the third level, it looks like this. If I have a tree cell here and a tree cell there, then I can combine them in a new tree cell that goes from this concatenation to that concatenation. And oops, I scrolled. And the last one that you get is again by the binary action on paths, but now using the previous one. So every time you use the previous one, and here I use this white bullet to get my third concatenation operation. If I have a path from alpha to alpha prime, so let's say this one is alpha, this one is alpha prime, I get a tree cell between them. If I have a path from beta to beta prime, then I can horizontally compose alpha with beta, and I can horizontally compose alpha prime with beta prime, and I get a path from that horizontal concatenation to the other horizontal concatenation. And you can continue this. There is a fourth one at the fourth level, and so on. So if you want, you can make that precise with co-induction. I did also formalize that using globular types, but I found it for my formalization to be more helpful to work with the concrete thing than with than taking it out of the co-inductive type each time. But maybe that's just my lack of experience with co-inductive types. So each pair of them, we get 3 operations. This one, the white bullet, and the star. Each pair of them will satisfy an interchange law. And that's going to be important because we will use these interchange laws to get to the end result. So the first one uses the pair consisting of the black bullet and the white bullet, and we already know this interchange law is just one level up. But it looks like this in the diagram. If I take the ordinary composition of these 2 tree cells and these 2 tree cells, and I horizontally compose those, although it's drawn vertically here, then I can interchange the order in which I do that. But I can do this with any pair of them. So the next one will be with the third concatenation operation and the first. So if I, so here these 2 are composable with the first concatenation operation. These also, but this one, I can compose it with this one using the third concatenation operation. So let's say this one is sigma and tau, and this one is nu, and this is phi. Then I compose them first with this way, and it's the same as composing it that way. There's a remaining one is going to be a bit funny because it doesn't type check if you do it naively. And it's the coherence law where I interchange the second and the third composition operation. So let's look at the types of these things. I have sigma is here, and tau is down here, and I have nu and phi. And first I horizontally compose this sigma and tau. So that's this composite. that is going to be a path from the concatenation of alpha gamma to this beta delta, and the same for this new sigma. It will go from here to there. So this path goes from, remember that the star is defined as the binary action on paths of this operation. So I have a path on this side that goes from here to there. I have a path on that side that goes from here to there. And this is the binary action on path of that operation. So that's why this path goes from there to there. And it's the same on the other side, but it's with the operations interchanged. That's why there is a problem. So if I just interchange the order in which I use the operations, the third and the second one, then my path will have a different type. So I have to state the interchange law as a commuting square, and this is where a lot of trouble is going to come from in my came from in my code, because now I have to deal with this interchange law at a lower level all the time. The good thing is that if I do this in a loop space where this alpha, gamma, epsilon, and eta, and beta, delta, zeta, and theta are all REFL, then this path is also REFL. And then this then I can just state that this one is that one. So it will be then easy. That's where the simplifications are going to come from. But the fully general form is this. So in this diagram, I show all the ways to concatenate let's see, I can, oopsies, whoa. So there are three ways, there are three interchange laws. One is for this part here on the left, or on the right side too, that's the same. One is for like the upper part, and the same one for the lower part. And there's an interchange law that takes 1 3 cell at each from each part there. That was the last one. And now I can say, but I can combine them all, and what should happen if I do that? Then something should commute. That's the one that's a bit hard to state. But when you simplify it to the third loop space, then it's just a hexagon. So it's easier to understand because things type check better in the third loop space. So here, what happens? I have the ordinary concatenation, then the second one, and the third one. I can apply an interchange law. Let's say I want to first do the second and the third, so the uttermost. I can just interchange them. Then this epsilon zeta goes to the other side, and the gamma delta also goes to the other side. And now from this position, I can interchange the first with the third, and I can step like that. And then I can interchange the first with the second again, and this will get me here. Or I can first on each side, I can interchange the black with the white concatenation operation. And I can do that on the other side too. Then I can interchange this first one with the third one to step in this way. And finally, I interchange the second with the third on both sides, and I arrive at the same point. Then you get a hexagon, and that hexagon commutes. And the reason it commutes is because there's the more general way to state this like hexagon, but it's not going to be a hexagon. It's going to be way more complicated because it has this extra. You have to deal with the fact that things don't type check if you generalize it. what was I going to say? Yeah, so you have to generalize this, and then you can use path induction on this alpha, beta, gamma, delta, epsilon, and so on. I'm using the whole Greek alphabet here, but they can all be made reful, and then it commutes by reflexivity. So that's how it goes. Why am I interested in this? Well, I'm gonna use it to derive the solipsis, and now we're almost there. I'm gonna use this hexagon to get 4 commuting triangles, and to get these triangles from the hexagon, I'm gonna show that on the whiteboard here in one case. But let's first say why do these triangles help? So here I have commuting triangles in third loop spaces with, at the bottom row in each of the triangle, all combinations of S composed with T in any order. So I'm just gonna tell you first why I'm interested in having these triangles. That's because I can use them to derive solipsis. So it's a statement that S Ekman-Hilton ST, which goes from S composed T to T composed S. And if I compose that with this Ekman-Hilton path TS, which goes from TS to ST, that is reful. So it goes from here to there. And remember that in the proof of the Ekman-Hilton, we stepped through the other composite. It looked like we didn't do anything, but we said it did something. And then you step to the ordinary concatenation again, but now it's reversed. And you do the same proof again. So now you step to the second composition, and then you finally go back. And the reason this long composite is reful is because these triangles here commute all of them. That was the previous slide. Here are these 4 triangles. These 4 triangles are here too, in a different order maybe, but they're all there. And these sides are the same here. So going from here to there is the same as going through the vertex of this triangle, but that's going through a path and then the same path back again. So that's reful. That's how solipsis works. And I have half an hour, so I want to show you, at least for one of these triangles, how you get it from the hexagon. So the idea is, so now I'm gonna stop sharing my screen. That's the risky part of this talk, because maybe I don't get it back again. There we go. So do you see me? Okay, great. So we have this hexagon and we want to use it to, great, I can even see myself have some feedback, to get this triangle. And here we had this alphabet. We are using the whole alphabet of Greek letters to write down some crazy concatenation of things in the third loop space. And now what I'm gonna do is, okay, so there are 8 positions to fill. Oops. I'm gonna align this better. Let's see.
If we're going to need to read the details of that, you'll need to write it a little bigger.
Oh, thank you for saying that. Hopefully it will. So. Okay, so this is what the shape of that first concatenation looked like. It had the third concatenation on the outside, then the second one in the middle position, and the first one on these 4. And now what you can do is you can choose like a position, maybe here. I'm going to put an S here, and I choose the opposite position here. I'm putting a T here, and all the rest I'm going to choose it to be a raffle. I'm going to write raffles as 1. And now I'm gonna observe that okay, this thing here with the unit laws is gonna be 1. Oops, which one is it? S composed with 1, and then 1 composed with T, and that is actually S star T. And this was always on the top of my triangles, S with the third composition of T. And I'm gonna get the other part of the triangles on these corners here. So ultimately, the reason why this triangles commute in this statement is because there's a hexagon in the middle somewhere. So let's see how this works. We want to interchange this second one with the third one. So let's say 1 with S, 1 with 1. 1 with 1, and then T with 1. And let's say now I did the other 2, now let's do the inner 2. So 1 star 1, S star 1, then 1 star 1, no, that's wrong. 1 star T maybe, and then is this still visible, or is it not useful to do this? It's somewhat visible. 1, 1. Okay, so here I will observe that this is just S star 1, and then 1 star T, and that is S composed with T. So we already have the other one. And here is the same. This is 1 composed with S, 1, and then, oops, this is a T, and then with 1. And that is S composed with T. And so there's one law is, so here we have the same one. So here we have to show that that the site commutes, but that's by a unit law that I mentioned. And here we have to observe that one of these sites commutes. So basically, I'm not going to do this because it's going to take me too much time, and I have 20 minutes left. Basically, the whole argument will be just I put in this hexagon. I chose 2 positions where I have my non-trivial loop, and I choose raffle everywhere else. Then I'm going to do a big diagram chase, and I get my triangles. And I'm going to do that 4 times, once for each triangle. But let's move on. So that is portion of the screen. Is my screen back? Okay. So that is also where I'm stuck in the formalization. I mean, stuck. I didn't do it. And this I will expect to explode my code by another 1,000 lines of code at least, or maybe more. That's why it's good that Christina has her proof, and this proof is probably, I'm not even sure if it's worth worth formalizing now at this point. But at least it's like for me, it's like still on paper, a clean way to prove ellipsis. That's why I wanted to show it. Okay. So now I was at this point, and yeah, I don't hear you very clearly, but you can ask.
In the previous slides, maybe this is a silly question, but does the proof also require like this diagram, but the other way around? So, or
yes, so there are two ways to prove ellipsis. Is that what you're suggesting?
yeah, are they equivalent, or do we need both?
Yeah. So we don't need both to prove the ellipsis, but you are right. There are two different ways to do it with this approach, because you can also put T star S and get some triangles here, yeah. So you don't need it just to get the plot, but just there are two ways.
Okay, thanks.
Great, thank you. Okay, so I'm gonna move on to the second part, and I was like thinking, now I have this ellipsis, and it's really about a fourth homotopy group of S3 that it has, that is the group of order 2. That's really what's going on. So the question is then, can I use this ellipsis in some way to encode the vibration over S3 so that maybe I can find a way to use ellipsis in the computation of that homotopy group. And I still don't know the answer to that, but at least it gave me some inspiration to to have another go at Zmod 2, and this higher encode decode method that I then arrived at, it's of course starts with the ordinary encode decode method, which I will all remind you of. And at the heart of it is a theorem that I like to call the fundamental theorem of identity types. And the reason is, when you're a homotopy type theorist, then like half of the time, what are you doing is characterizing an identity type, and it's with this theorem. And this theorem is Theorem 584 in the hotbook. If you like to look it up, it's stated a little differently there. I simplified it. I made it unary, whereas in the hotbook it's with a binary relation. It's a little easier to understand when it's a unary relation. But it's essentially Theorem 584 in the hotbook if you want to look it up. And it's a little strange because it's a really an important theorem, and it's buried so far in the book that people don't even know about it. Anyway, the theorem is a way to characterize the identity type of a type A at the base point little a. So and if I want to characterize it, I want to come up with a new family that I understand better than the identity type. This family is B. It's like an encoding of the identity type. And what then do I need to show that it's equivalent to the identity type? That's what part 1 says. B is equivalent to the identity type. And the answer is you need to show that the total space of B is contractible. And then you get this equivalence here. And you also get a variant of path induction for B. And the formal way to say that is that it's an identity system. So if you're curious, you can look that up in the hotbook, what is an identity system. And I think, again, it's stated in the binary way. It's a little easier to do it unary, but that's the way it is. Okay, so this encode decode method can be used to characterize almost any identity type, and you can, in principle, iterate to also characterize higher identity types. And you can have some success with it, but it's really not so practical to do that. And that's why I wanted to have a different encode decode method that allows me more directly to compute higher homotopy groups of types. because this one is very good for the fundamental group, but not super useful for higher homotopy groups, at least not in my experience. So here is the theorem that that then I found. Now let P be a family over a pointed type, and this family should be of n+1 truncated types. And it's not over X, but it's over the n truncation of X. That's important. Now, if you can fit it in a commuting triangle like this, so I can lift the unit of the n truncation against the projection. And if I can show that this lift is n+1 connected, then that is great, because that implies that the fibers of P are these Eilenberg-MacLane spaces. And I'm gonna give you the proof. But what is here at the heart is this fiber sequence that unfortunately I didn't display here. But I can go from the n+1 truncation into the n truncation. And the fiber of that map is this Eilenberg-MacLane space. So if I go from the n+1 truncation into the n truncation, the fibers I know, they're these Eilenberg-MacLane spaces. But here I go from a different type into the n truncation, and the theorem says, well, under the condition that f is n+1 connected, then it's going to follow that this type here is equivalent to the n+1 truncation of X, and then a consequence will be that the fibers of P are the Eilenberg-MacLane spaces of the homotopy group. So let's see the formal proof. I mean, just a sketch of the proof, because this is presentation. So the observation is, okay, the individual P of X's, they were n+1 truncated. So if I take the sigma type, it's also going to be n+1 truncated, because this one is in particular n+1 truncated. And also, any n+1 connected map into an n+1 truncated type is going to be an n+1 truncation. It's going to satisfy that universal property. So from the conditions, from the fact that this one here is n+1 truncated, and this map is n+1 connected, it follows we get this commuting triangle here, and you can arrange it, and you can then show that this commuting triangle also makes this triangle commute. But if we have a commuting triangle like this, that means that the fibers of this map are equivalent to the fibers of that map, and that's the reason why we get this equivalence here. So I suggest that this is a way to compute the higher homotopy groups of X, because now what can you do? You can define this P. P is like your encoding. It's not directly an encoding of the n+1 identity type of X, but it's going to help you to compute these homotopy groups, because we can define P into the subuniverse of kg n+1s if we guess that the homotopy group of X is G. Then if we show that there's this commuting triangle and make sure that this F is n+1 connected, then we can apply the theorem and say, but then the n+1 homotopy group of X must be G. So that is the method that I am suggesting. And so what do you need for this to work? Well, we need quite a lot actually to even apply this, and I didn't do all of it yet. I'm planning to it, but this is where it's really work in progress. We need a new universal property of the n truncation with respect to all to the n+2 types, and Nikolai Krauss did something like this, but he gave the universal property of the n truncation with the n+1 types. So that's almost there, but it's not quite the same. And what I'm hoping for is that we can generalize his universal property, bump it up one level, and get a new universal property, because it will be useful in this higher encode decode method. I think we also need a dependent universal property of the n-truncation with respect to the n+1 types. I think also Nikolai only did the normal universal property, so it will be nice to generalize it to a dependent universal property. This one is a little easier. I mean, about both of them, I have ideas about how to do it. I was just not ready to show it in public yet. And we need a good handle on the type of types that are merely equivalent to an Eilenberg-MacLane space. And this type was studied by Louis Kokolai in his paper on the nilpotent types. And so there are some hints there about what this space is. But in the last 10 minutes, I'd like to, since my motivation was about computing pi4 of S3, the G here is going to be C mod 2, and then we can just use the fact that C mod 2 is very simple to directly say something. So we are arriving at part 3 now. And the theorem is a recursive formula for saying what KZ mod 2 is. The recursive formula is that K Z mod 2 n+1 is equivalent to the type of all K Z mod 2 n's. And this one I will like to prove it, and that will be the end of my talk. So in order to prove it, I'm going to use a theorem from Buchholz, Dorn, and Rijke from our higher group theory paper. And if you have two groups, G and H, then the type of group homomorphisms is equivalent to the type of pointed maps between their classifying spaces. Or if you go to higher KGNs, then it's just pointed maps between those higher KGNs, but then G and H must be abelian. And you can also do this with group isomorphisms. Then instead of an arbitrary map, you just get an equivalence. So it's this particular statement that I want to use in my proof. The proof is here. Okay. So we're claiming, let's repeat the claim. We're claiming that K Z mod 2 n+1 is the type of all K Z mod 2 n's. So what do we need to do? We need to show that this, so we already know that this type is connected because it's basically connected by definition. What we need to show is that its loop space is K Z mod 2 n, because the loop, this is the connected type of which the loop space is KZ mod 2 n, by definition, basically. So we do that with the fundamental theorem of identity types that I showed you earlier, the one that characterizes ordinary identity types. And we're going to show that this type here is contractible. So the type of all x's that are in this subuniverse equipped with a point should be contractible, because then we know that that the loop space of this type is at the base point is KZ mod 2 n, and the loops will be then this x here, which will be KZ mod 2 n. So that's what we need to show. So the base case, it's not really a proof by induction, but more by case splitting on n is 0 or non-zero. And the case for 0 is a theorem from Buchholz and Rijke in their paper on the real projective spaces. There we analyzed what is the type of two-element types, and this is a generalization of that fact. So now we can assume that n is bigger than 0, and in particular, it follows that KZ2n is connected. If it was 0, then it was 2 points that's not connected. So you're going to use that it's connected. So at the center of contraction, there's the obvious choice. You have KZ2n we have the identity equivalence here, and we have the base point, so that's the center of contraction. So we have to construct the contraction now. We're going to say that the space of paths for this contraction is contractible again, because that's a proposition. So we want to construct then an equivalence from okay, so given an x, which is merely a KZ2n, and given a point in x, we want to construct an equivalence with KZ2n such that the base point is mapped to x. That's what we want, but we're going to show something stronger. We're going to show that this space is contractible. Why would we show something stronger? Is because contractibility is a proposition, and here I have a propositional truncation, and my x's are connected. So this x also is merely equal to the base point of that. So because I'm showing contractibility now, I get to get rid of these truncations. I get to assume that I have an actual equivalence, and I get to assume that x is equal to the base point, which means that I have to now show that this other type here, which is simpler, is contractible. This is the type of all self-equivalences on KZ2n that map the base point to the base point. And why is there only one? Well, that's by the lemma that I showed. By this lemma, this is equivalent to the type of group isomorphisms from Z2 to Z2, and there is only one group isomorphism, so that is the end of the proof. So let's just mention two corollaries before the end of my talk. The first one is that the automorphisms of KZ2n are really simple. They are the type of automorphisms on KZ2n is just KZ2n again. So you have this this kind of domain equation, but with equivalences, not with function type here. So that is just a curiosity, I guess, but also a more important point. We want to use this in the computation of the pi4 of S3. And now we want to use this to construct a fiber sequence of which the fibers are KZ2-4, because if we want to apply our theorem with the fiber sequence that already we know that here this is KZ2-4, then we apply the theorem and say, okay, but this C mod 2 is going to be equivalent to the fourth homotopy group of S3, and that's one way to prove that, to get that isomorphism. If we have this connected map into it. So the tree truncation of S3, that is this Eilenberg-MacLane space here. It has only one non-trivial homotopy group, and we want to describe this fibration. So this is a map from S3 into the universe of all KZ2-4s, and we have just shown that is a KZ2-5. So what we want to get this is to describe a map from KZ3 to KZ2-5. And this is really nice because this is an element in the fifth cohomology class with coefficients in Z mod 2 of the space KZ3. So what we're doing here is we're reducing the computation of the fourth homotopy group of S3 to a computation of a cohomology class. And this, of course, is classically well known again. So we just got there differently using type theoretic methods. But here, to get this and to get that this E is the fourth truncation of S3, the classical way to do that is again with the Serre spectral sequence, which we have formalized in homotopy type theory. So maybe we can apply it. but also that it preserves the product structure, and so it does get a little bit more complicated there. And I certainly haven't done anything in that direction, but I think this looks really promising because all the ingredients are already in homotopy type theory. We have this Eilenberg-MacLane space. We know how to talk about cohomology. We have this spectral sequence even, so we can try to mimic that classical computation that you can find in bottom 2, because now we have found a way to reduce the computation of pi 4 of S3 to this cohomology class. So yeah, that's it for my talk. Thank you.
Okay, thanks very much, Egbert. So please join me in silently applauding with your microphones muted. Visual applause. And if you're watching this on YouTube, this is when you hit that thumbs up button if you've watched this far into the talk. All right, so now we open the floor to questions. Please just unmute yourself and feel free to ask a question.
So I was wondering for the first part about the solipsis, whether it was one of these things that are easier to tackle if you don't prove the globular case, but instead you generalize it a bit and prove instead a statement about squares and cubes. I think there's this paper by Dan Licata where he shows that some coherences are easier proved when generalized to cubes instead, even if you don't use cubical type theory, but just Buchard.
Yeah, that's a good suggestion. But that is really about path overs though, and I'm not encountering any transport at all. So the transport is not really the problem. That doesn't mean that there are no simplifications using dense methods, but I just haven't thought about it. Yeah, I guess that's my answer. Good suggestion, thank you.
Egbert, did you look at the classical proof of the solipsis, and what does it look like? How does it compare to your proof?
To be honest, I haven't. I just saw that talk by Vickery and thought, okay, I can do this by myself, and that's what I did. Sorry.
Do any of the insiders here know the classical proof? Maybe one of the Dans? No?
Well, I mean, the classical proof of pi 4 of S3 doesn't really go through the solipsis directly. So it's a separate argument that's somehow encoding the same fact. And I don't, off the top of my head, know how that part of the argument goes.
Didn't Jamie in his talk, I don't remember that talk, say that it was somehow goes back to Poincaré or somebody like that, the solipsis? Egbert, do you remember? You must have at least listened to Jamie's talk.
Yeah, I was there. I don't remember him mentioning Poincaré.
Well, or maybe, you know, somebody, Heinz Hopf, or somebody new.
So Hopf is definitely, again, related to the computation of pi 4 of S3, because the suspension of the Hopf vibration is again that non-trivial element in the fourth homotopy group. But, yeah, I don't know.
Okay, Egbert, didn't I teach you that when you give a talk about a classical subject, you have to start by giving the history of the classical subject?
Yeah, sorry.
So when you write it up, though, tell us, you know, something.
Yeah.
But anyway, it's beautiful to see it done in hot. So curious what the classical proof looked like.
Thank you, Steve.
Yeah.
that will teach me. I should not forget my lesson from grad school.
Can I ask about the last slide?
Yeah.
Okay, so if you come up with a cohomology class as shown, that will give you a family of KZ24s. But you do need to also have this connectedness property. You need the lift and the connectedness of the
Yeah,
lift.
that's right.
Do you know how to, if that translates to a condition on the cohomology class, or how you would know the next step?
Yeah. Yeah, so I can only guess here. So it's gonna imply that the cohomology class can be like the 0 or something like that, because then you won't be able to prove that connectedness. But I didn't formally work this out. But it must be something like that. Yeah. So let's go to the yeah. So here the x is going to be S3, and it's going to be 3, and this is going to be the type of all Allenberg-MacLane space. So this is going to be the KG25, and yeah, I don't really know what is going to be involved in showing that it's connected. So when I try to reconstruct just the fundamental group of the circle, then in showing that that this F is connected, there you saw, okay, so this is the point where you get to the actual calculation, also where the traditional encode decode method gets you to some point where you have to actually do some actual work, and that's the same kind of work again, even if you try to shoot this cannon at this universal cover of the circle. So yeah, this is where the technicalities lie, probably.
Okay. I think the dotted arrow will exist automatically, because the cohomology class that you get on the 3 truncation of S3 will have to pull back to be trivial in S3, because S3 doesn't have any 5th cohomology.
Oh, yeah.
So that means the pullback of this type family will be a trivial family, so it'll have a section.
Oh, I think I noticed that once. Yeah, thank you. Yes, you're right.
So I think the existence of F comes for free, although maybe it depends on a choice of some null homotopy.
Yeah, that's right, because at each stage, the only choice you can make is always the trivial choice. Yeah, so you have to prove this connectedness.
Yeah, I don't see how the connectedness will follow quickly, but maybe there'll be some way.
Well, it should be difficult somewhere. It's probably at that point.
Okay, next question.
Okay, I'll ask another question. Do you have it looks like you have a proposal for a maybe alternate construction of the Postnikov tower using this kind of iterating your analysis of these
Oh, so yeah,
truncations.
yeah. So the starting point of this higher encode decode method is basically the Postnikov tower, because I'm using the fact that the fiber of the map from the n+1 truncation into the n truncation is the KG n+1. Right. So I'm not reconstructing the Postnikov tower. I'm using that factor already. Okay. And I'm using that the Eilenberg-MacLane spaces exist.
I see.
So yeah, in that sense, it's a little bit more advanced. Yeah, because even the existence of the Eilenberg-MacLane space, I believe it already uses Freudenthal suspension theorem. To prove that they satisfy the correct properties.
Right. Yeah.
So it's a little bit more advanced, but like at this level, it's not such a difficult theorem. That's just a one slide proof.
Well, maybe I can make a small comment on that. I mean, I gave a talk 2 years ago at the workshop in CMU, where I also constructed the Eilenberg-MacLane spaces using mixture structure on this type of gerbs. These are the Eilenberg-MacLane gerbs at dimension n+1. And if you add a band, a banding to them, so you say that it must be after one truncation an equivalence to the band of G, then you get the type of KGn+1s. And then you get that type becomes KGn+1.
Yeah.
So that's also connected to giving these cohomology classes. You have to give a gerb together with a banding. So it might be worth looking into that.
Yeah, maybe you should give that talk again.
Maybe I should write it up. I'm writing it up.
Yeah.
I should maybe publish it sometime.
Yeah. We should have a talk sometime again soon. Cool. Thank you, Ulrich.
Okay, any more questions? All right, well, if not, let's all thank Egbert again. And our next talk and the last talk of the semester will be by Ulrich, who just spoke. And his title, I had it here somewhere, Co-Cartesian Families in Simplicial Type Theory. So I hope to see you then.